In this section, we're going to talk about Advanced System Administration. The following topics will be covered: the YaST Security Module, Backup and Recovery, Software Libraries, General Server Health, Monitoring Overview, and Control Groups. The YaST Security Module. In this topic, we're going to be covering how to work with the security settings of the YaST security modules, the pre-configured security settings available there, and how to work with custom security settings as well. YaST has its own security center and hardening module. This is a central hub or clearinghouse to configure security-related settings that are particular to SUSE Linux Enterprise. We can work with things like logins, password creations, password requirements, boot permissions, user creation, user default during creation, default file permissions, and so forth. It is launched simply by going to the YaST Control Center under Security and Users and Security Center and Hardening. It always starts with the security overview as the first screen that you see. Here is an example of that security overview. Notice that on the left we have navigation, on the right we have the settings particular to the thing selected on the left, and we have links to change or modify those things that are listed here, as well as a contextual help link to give you information about what each item does and what best practices might be used. So let's understand the pre-configured security settings. Now we can use this module as described. If we click the predefined security configuration under this security module, we can select predefined settings or use custom settings in order to have our own direct control of what's going on SUSE Linux. So what are the custom security settings that we most likely would work with? Well, if you select the custom settings, it would be any of the items on the left that you change will automatically be moved or be a part of the custom settings you've defined. In other words, the predefined items up above custom setting here would give you a preset and already configured way of hardening or defining your security profile for a machine. If you make changes on the left side, it will automatically switch to custom settings as you have deviated from the predefined security settings. In other words, this link doesn't necessarily change anything if you put the radio in custom settings. By default, when you make a change that's outside of the other settings, it will move to custom settings as well. So, what changes could we make? Well, we can go in and change the password settings, such as minimum acceptable password length. 5 probably isn't good enough for most enterprise environments. We let you decide though. You can come in here and define what is okay. How many passwords are we going to remember? What encryption method would we use for our passwords? We can also set the age on passwords and how many days before the expiry of a password do we warn you about that change. What about boot settings? Well, how do we interpret Control-Alt-Delete? By default, if you're in a sudo terminal and you do a Control-Alt-Delete on a SUSE Linux box, it reboots the box. You can also tell it to do nothing or to halt the system. We can also work with the graphical interface, the GNOME Desktop Manager Login Manager as well, and make changes to the way it works. We can also work with other settings that are specific to the functioning of a SUSE Linux box as related to booting. What about login? What is the delay when someone enters an incorrect password? It's 3 seconds by default. You can change that as well. When adding a user, what about group ID and UID values? What are the defaults? What are the minimums? How are those defined? We can see those and change those as needed here as well. And of course, there are some other miscellaneous settings that we can work with to define our security profile in this hardening center. In this lab, we're going to take a look at the YaST security module in SUSE Linux Enterprise. If we go out and take a look at the contents, let's just look at the etc systemd system directory. Just to look at what's in there, you'll notice there's no entry currently for the Control-Alt-Delete option. So if someone presses Control-Alt-Delete, what's going to happen? Systemd is what interprets that. So let's make a change and look at how that affects things. So if we go into YaST and go to the System Tools under Security and look at the Security Center and Hardening, we'll notice that there's, on the left-hand side, there's a Security and Users section. And if we look underneath the predefined security configurations, you'll notice that we have custom settings defined. That's fine. And then, of course, we can also see things like password settings and so forth. You'll notice that SHA-512 is currently selected. Let's just make a couple of changes just so you can see how these can be implemented. That's fine. We've got that selected. Let's go to boot settings. Control-Alt-Delete currently is set to do a reboot. We're going to change this. We're going to make it so that a Control-Alt-Delete executed from inside of the sudo terminals is going to cause a halt or a shutdown with a -A or halt on our system. So we go ahead and we click OK. We've now made that change. Now, if we take a look at the directory, if we do an ls, let's say -L here, just to give us all of the information, you'll notice that before we didn't have a Control-Alt-Delete reference here, but in this location, now that we've made that change, you can actually see that it references the power off target for systemd. So if we press Control-Alt-Delete inside of a sudo terminal, it will shut all the way down. Okay, so that's part of what's been done for us. Notice we did also change the SHA to 256 instead of 512 for the encryption of the passwords. Now that one's a little less obvious for us. We don't really notice that change, but that's also been done as well. So now we're going to just go over to a terminal, and you'll notice that the terminal, if we're in this terminal, let's say we get in here, if we do a Control-Alt-Delete, what's going to happen here? I think it's going to be pretty obvious what's going to happen. Yep, it's exactly what we expected. It's going to shut down that machine. But that's what we told it to do. Now, that's a pretty simple use of our YaST security module, so you can see how that works. We're going to go back in and change those back out, but now you have an overview of what that YaST module looks like. And working with SUSE Linux Enterprise, we try to make it as interactive and ease of use as possible while still giving you all of the functions of Linux. Backup and recovery. In order to fully understand the backup and recovery schemes and methodologies in SUSE Linux, we need to talk about Snapper, as it encompasses the majority of the predefined backup profile for a SUSE Linux box. Let's talk about what Snapper is first, because you may not have seen it before. Snapper is a tool that provides, given the right circumstances, the ability to perform rollbacks of individual files or an entire subvolume or file system. Now, there are some prerequisites for this. The Better or ButterFS file system is the recommended version that we would like you to use, or file system to use, on a SUSE Linux box if you're going to be using Snapper. Although you can use LVM with thin provisioned logical volumes if you so choose. Also, you do need SUSE Linux Enterprise 12 and newer in order to do a boot from snapshot function, which allows you during the boot menu to select a previous version of a volume and use that as your boot volume. So what's included in a snapshot? Well, the root file system by default is included, but there are some directories that are not included, both for practical and technological reasons. The first and the biggest subset, if you look through here, are things that you're probably not going to want the constantly changing information inside of those directories to be captured every time. As a result, those are removed from the snapshot. Now, you can go and configure this to include these directories if you want to. This is only the default settings. Feel free to customize as you need to. So, what are the types of snapshots? Well, there's a timeline, which is turned off by default for root. It's taken hourly. That's what a timeline is. And the last 10 daily, monthly, and yearly snapshots that are part of a timeline are kept. Again, this is disabled by default, but can be turned on as necessary if you need periodic ones. There's software management types of snapshots. When you invoke the libzip library when doing software management, the zipper command or inside of the software management tools found in YaST, it creates a before change and after change. We call those a pre and post pair. Those allow us to roll back should a software install go awry or not have the desired effect. Anytime you go into YaST, you also, and open a module, it will create a pre and post pair as well. This is again so that before the change and immediately after a change that you implement through the YaST modules, those will be preserved. So you can have a rollback or a backout plan or method if necessary. We can also trigger a manual snapshot as well from the command line or through the tools available through YaST. So let's talk about the configuration of Snapper itself. In the etc directory, there is a Snapper subdirectory with a configs subdirectory of that. If you were to use various tools, the Snapper tool from the command line is listed here with the create-config and the path you want to create a configuration for, it will generate one for you. We can also list the configuration options there as well, and there is an example for the root volume. We can get a list of Snapper configuration files if we look inside of the etc sysconfig snapper file. And if you want to prevent a file from being snapshotted, you can also go and filter those files as well. Here's an example of what a configuration file looks like under etc snapper. If we look at this one, which is described for the root volume, you'll see that it has different types of things, and they've been broken up into colors here to make it a little more obvious. We have user permissions, those who are allowed to work with snapshots and the configurations. We have the number, so how many snapshots should we keep? We'd call those snapshot parameters. We have timelines, which are time-based snapshot configurations. And of course, we have the pre and post snapshot configuration items as well. So, what tools do we use for managing snapshots? Well, inside of YaST, there is a Snapshot Explorer that allows you to view differences between files, to create new snapshots, to view existing snapshots, and of course to work with all of the various components that come from maybe restoring an individual file or an entire volume as well. There's also from the command line a tool called Snapper that allows you to show, create, or delete snapshots and do rollbacks. You can also do differentials of files and see the differences between them. But also, the configurations and information about snapshots are kept in a quote-unquote hidden directory underneath each location where a snapshot directory or configuration is defined. Under the root volume, by default, it's the .snapshots directory immediately off the root volume. Inside of it, it has a list of directories that each one will represent a snapshot, and it will contain things like a descriptor of the files that have changed and other information that can be read and worked with directly or through these various tools that we've already talked about. Here is the YaST Snapper module itself. As you can see, we have various snapshots. They're defined by their IDs. That's on the left-hand side. These IDs simply are unique identifiers that we use either from the command line or identifiers that we could use here to say exactly which one came from what time period. They're a little simpler than putting in a date. Now we can highlight one, we can look at things inside of it, we can make some changes to the snapshots, and various other things noticed down at the bottom in the buttons. In this particular part, we've gone into a snapshot and we're comparing the differences between two files from the same file from two different snapshots. You can see in the red with dash 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 in front of it in the right-hand box, you can see that something has changed. This is the modify date for the time for that file, and then plus plus plus, which says this is what was added or modified. And then you can follow that same logic down below where we see the history and the last visited are being removed, but then we see the history and last visited being added with different values. This is indicative or typical of these kinds of changes that are made and captured via snapshots. And the snapper module makes it very easy to display. Now, if we want to, we can also restore a file from a snapshot. So we've configured, let's say we've found this file to be what we want. We select, yes, we want to restore it. You can do that in the bottom right-hand side. And you notice you can restore the file. You can restore from the original. You can restore from the second one. And it will pop up and give you a, are you sure this is the one you want? If you click yes, it will restore the file as you described. We can also, inside of the YaST Snapper module, create new snapshots. We click Create New Snapshot button, and we add a description, the type of snapshot it is, whether it's associated with another snapshot in pre and post format, and then we can give it some additional information about its cleanup and so forth. If we want to modify a snapshot, let's say we make a change, but the built-in description is too plain, we might come in and say YaST security -password or something like that to say we've made a change to the way that passwords are handled and this is the one after or before that change, whichever parameter you want to capture or remember as part of the description. Now the snapper command does pretty much the same things that are found inside of the snapper module. However, it's from the command line. So it requires the standard format and layout for both arguments and parameters. So the general snapper syntax is snapper, any global options, the subcommand or the command options that go with it, and any arguments that go with it. So as an example, a simple one, snapper space list, would list the snapshots for the root file system, unless of course you specify a particular volume other than root. By default here, it's going to be the root volume. To create a new snapshot, we would do a snapper create, -d put in a description, -t the type of snapshot, whether a pre or post number is going to be involved, and then the command for additional items if you want to. Here's an example down at the bottom. Snapper -c srv, create -d, description -c timeline. There we have an example of a snapshot being created of type timeline. Now, there are a bunch of other things that we can do with Snapper besides simply creating snapshots. We can do a compare of snapshots, snapper space status, and then two different snapshots, and it will give us a list of files that have changed. We can look at the contents of files using the diff snapper command, snapper space diff space the number of the snapshot, that's the ID, dot, the other one you want to compare it to, and then a space and the list of file or files you want to compare. We can undo a change on a file with snapper space undo change space and again the ID dot ID and then the file you want to undo or to roll back. We can delete a snapshot by using the snapper-c config, whichever configuration we're going to be using, delete, and then any snapshots you want to remove. Yes, you can use a range, as is noted in the command here. Now, snapper commands that we might work with also things like snapper get config to tell you how a particular volume or subset of volumes is being snapshotted. We can change the configuration from one value to another with a snapper-c config and a set config value, or we can use a create configuration as well. Now, working with snapshots, and we've described the YaST tool and the command line tool, there's also a directory layout that we can work with. Again, it's usually at the root of the volume where snapshots exist, in this case, the root volume. If you look at the info.xml file, as is highlighted here, you can see information that describes the snapshot. We can then go into other snapshots, let's say the number 2 snapshot, and we can see any files and directories that have been modified or worked with, and so forth. This becomes easy to work with as well as you familiarize yourself with those directory structures and what each of those files contains. Now, having created snapshots and looked at different things, what about rolling back a change? Well, there's a couple of different ways to do this, and it depends on if you are working with a specific snapshot you want to roll back to, or you don't provide one. The simple syntax is snapper space rollback, and then the number you want to go back to. And it creates 2 new snapshots and sets the default subvolume. So per default, the system boots from the default subvolume for the root file system. And the exact actions of this snapper rollback number command depend on whether a number is provided or not. If you do not provide a number, first a read-only snapshot of the default subvolume is created. A second read-write snapshot of the current system is created to preserve your current location, and then the system is set to boot from that snapshot. Now, this is useful if you choose to boot SLE, SUSE Linux Enterprise, from a read-only snapshot in the boot menu and want to make the system boot from this snapshot by default from now on. If you provide a number with the snapshot rollback number command, a read-only snapshot is created of the current system. A second read-write snapshot is created of the numbered snapshot, and the system is set to boot from the second snapshot. Now, this is only supported with Btrfs and requires a properly configured system, and by default, this is how SUSE Linux Enterprise is set up when you install. Let's talk a little bit about the mechanics of the rollback itself, and maybe a visualization will help. Before any rollback, this is what it looks like. We have various read-only snapshots, and we have a current read-write snapshot. In other words, the way the file system currently sits. If we issue a snapper rollback 2, read-only 2 being the target rollback that we're going for, the first thing that happens is that a new read-only clone is created. This one is, in this case, going to be called read-only 5. This is a capture of where we currently are in case we need to back out. We then take and do a new read-write clone based on the number that was given, number 2. The new read-write clone is then defined as the Btrfs subvolume default, so that the next time that we work with it, that's the subvolume that we'll be working with, that particular version. Then a new clone is created just to make sure that we've got a backout point from before the change and after the change as well, so we can recover to a certain point. To boot from a snapshot from the command line, and this is SUSE Linux Enterprise 12 displayed here, but works for anything after SUSE Linux Enterprise Server 12. If the system does not boot properly, we can select from the menu, start the bootloader from a read-only snapshot, select the one that we want, and boot the system accordingly. In this lab, we're going to look at the snapper tool and using it to roll back changes made on a SUSE Linux machine. To begin with, we're going to use the snapper tool as root in a shell. We're going to do a snapper list in order to show the currently available snapshots that are available. If we wanted to, we could go back to a version of whatever snapshot we wanted, whatever specific to a file or to an entire system state. This is one way to look at the list of snapshots. There are a couple of other ones that we can look at. If you do a mount and grep for snapshot, you'll also see that there are a couple of subvolumes that are related to snapshots. In this case, we have a snapshot that is being used as our read-write volume. So we're making changes based on this one. And if we wanted to, again, we could use this as kind of our baseline. In fact, we're going to do that. There's another location that we can look as well. If you do an ls at the root of the volume, if you take a look, you can see directories. Now you'll note that these correspond with the snapshots that are being used or that are listed in our snapper list above. Okay, so we've got multiple tools for looking at or seeing snapshots. Let's create a snapshot, then make some changes and see how snapshots can be used to roll back a file that we want the original version on. So let's start with the snapper create command, -C. We're going to give it a type of timeline, and we're going to call it snapshot. Okay, like that, my snapshot. So we create the snapshot, and if we do a snapper list, you can see that 30 is now the snapshot, and the description is listed as my snapshot. Okay, so we know which one that is. Now let's make a change, a simple change. We're going to edit the etc hosts file, and down at the bottom we're going to add just an entry, 17.2.25, and we'll call it server 5. Okay, so we've added, we actually added 2 lines, right? The space there, the empty line, and then this entry here. We'll go ahead and save that. And now we're going to go into YaST. There's more than one way to do this. We're going to look at a couple of different ways to do this. We're going to go into YaST and look at the snapper module. And this is going to list or show our available ones. It shows the one that we did from the command line that we took. That's my snapshot here. But you'll notice we also have another one created. This was generated because we opened a module in YaST. It takes a snapshot so that any changes can be rolled back if we make those changes. Okay, so that's happened. That's good. So we're inside of it. Let's actually take a look inside of this my snapshot. Let's look at changes. What it's going to do is going to say my current system compared to what things looked like when that snapshot was made. And the only change to the system that was made was the change that we made. And if we highlight it and show that, you can see that in red we have a change to the timestamp, the modified date. Okay, that's different. So we have the original in red. The blue shows what was added. The plus signs out to the side show us changes. And then we have the empty line and the reference to server 5. Okay, what we expect to see. All right, let's do the snapper list again over here. And if we do something like snapper diff to do this same comparison in a command line or from a command line, snapper diff, and then the number of the snapshot and the one that's flagged as current. In this case, it's 0. So the my snapshot that we want to look at is 30, and then we put 2 dots and the one we want to compare it to, the original or the current in this case, and it will pop up and do the comparison. It basically shows us identical changes, right? We can see that. So we can look at it from the command line. We can go into the snapper tool and look at it as well, should we choose to. All right, so now we're going to roll back the changes on that particular file and see what happens. Now that we have compared and we see that changes have been made, let's roll back some changes on that. Let's go back over to YaST. And we're going to, with the host file selected, we're going to click Restore. And it's going to say, are you sure you want to use this version instead of the current version? We're going to say yes. It's going to say, okay, we did that for you. And now we're going to come back over here and we're going to do a cat of that etc hosts. And what we should see is the reference to server 5 is no longer there. I mean, if we scroll up, we can see, in fact, we don't even have to scroll. You can see server 5 was listed. It's now gone. That's what we would expect it to do. Now, when we do a snapper list again, and we take a look at what's happened, if I come back here, I'm done. I've finished what I wanted to do. If I close out of here and do a snapper list on this again, you'll notice that what's happened is I have a pre and post pair, these two bottom entries. Now what's happened? The pre one, as I pointed out before, was created when I went into the YaST snapper module. Anytime you go into a module in YaST, it creates a snapshot, just in case any changes are made, so that you can roll back if you find that any changes that were made were bad or inappropriate or need to go away. After the changes are made, there's another snapshot that's made so that you can go back to the last version just after those changes were made as things roll forward, and over time that might be useful to you. And we can do a comparison between those two. In this case, the numbers are 31 and 32. Okay, so we can do the snapper diff again, and we can do 31.32 and compare them. And sure enough, it shows that the changes of the etc host file where server 5 was referenced indeed are there in 31, but are not there in 32 after our changes were made where we rolled it back. Now, there's more information that we can get about individual snapshots. So if we do, let me clear the screen here. If we do a less on .snapshots and we say, let's see, 32 was the post, and we look at the info.xml file, it shows you information about it. It shows you when it was taken, etc. Instead of looking at info, if we look at the file list 31, the companion snapshot, the pre-snapshot, this being the post-snapshot, it says, oh yeah, etc hosts file was the one that was changed. Okay, so we can do it from the tool if we want, inside of YaST using the module if you want, but you can also get all this information just by browsing out and looking at the appropriate location in the file system. Okay, so we're going to make a change to the NTP configuration just to capture changes in our snapshot. So NTP, we'll look at the NTP configuration inside of YaST. We're going to go ahead and say now and on boot, and we're going to add a server. We will add something like, let's use a default value. Let's do 0.pool.ntp.org. Okay. And we can just hit OK. We don't care if it actually works. It's just something for us to put in there and capture. So we're going to save that. And now we're going to come back and we're going to do a, we can do this inside of Snapper too. Let's just do that. Snapper. There's Snapper. And you'll notice again, look at this. We have yet again a pre and post pair that are showing up, 33 and 34 for the NTP changes. Again, before we made our change is 33, after we made our change 34. All right. So if we want to, we could highlight these, we could do a show changes, and we could look in here. Now, what exactly was changed? Well, the entries for the reference to the NTP server we're going to synchronize with has been added to cronny.conf, as well as systemd, we've added the cronyd.service where we told it now and on boot, go ahead and start this service. So that had to be added as well. So let's do this from the command line. Let's just do a snapper list like this, and you can see sure enough, 33 and 34, and of course 35 because we went into the YaST module for Snapper as well. That showed up just in case we make changes and keep them. All right, let's make some more changes and do some more snapshots and just kind of see how this works get a little bit better understanding of it. Let's do an RM of etc scal, and let's get rid of something like the mudrc file. This is a default file there. Okay, so we've deleted that. Now, if we do a snapshot of the, let's say 34 was the post. Actually, let's go 35. Oh, whoops. We want to do that. Let's do status instead of 35.0, 0 being current. Snapper status. 35.0. Okay, like that. We can see the thing that's changed is mutrc. Okay. So we can also do from, and we didn't roll this back from the command line. We could do that. We could do a snapper undo change, and then we do 35 ... current. Oh, whoops, not current. Current is 0, sorry. And then we do what file we want back. In this case, it's etsyscale.mutrc. Okay, there you go. It created or added the file back. Now we can do a snapper list, and we need to look at our original snapshot. So my snapshot was the one that we created originally. And let's go ahead and just delete that. So how would we do that? Snapper, delete, and then the number. In this case, it's 30. And snapper list, and there you go. My snapshot is gone. And that's just fine. So that's working with snapshots and using the snapper tools, both from the shell, but also from inside of the snapper module for YaST. Now we're going to create a second ButterFS file system to test snapper with. To do so, we're going to fire up YaST, and we're going to go into the partitioning tool. It's called partitioner. And yes, we know what we're doing, or we pretend to. And we're going to go in and make a change. We're going to highlight VDB, and we're going to add a new file system. So we're going to click Add. We're going to let it be the maximum size. So we'll hit Next, and it'll be data and ISV. And we're going to format it as ButterFS. And the mount options, we're going to call it Data1. And then we'll just go ahead and click Finish. That should go ahead and create that for us, or prepare us for that. Then we'll click Next and Finish. And we've now created our partition to work with. Now, in order for us to interact with this new partition that we've created, we need, from a snapper standpoint, we need to have a configuration file for it. Now, this is a simple thing to do. We type snapper -c data1, and then we do create config is the command, and then the location or the mount point where this is going to apply is data1. Okay. Now, if we take a look at the etc snapper configs data1, you'll see that it has indeed created one for it. Okay. So that's one way, is we can go in that etc directory. Or we can go and do a snapper list-configs like this, and this will show us the configuration files that are currently available to us. Now, we're going to create a snapshot. This is the first one created for data1. We're going to do a snapper -c data1 create -c timeline and data1 snapshot. Okay, all right. So there we go. We've created that. Now if we do a snapper -c data1 list. Now, why didn't I just type snapper list? Okay, well, since this is not part of the root snapshot pieces, if we do a snapper list, it's only going to show us the snapshots on the root volume. Since this is a new volume we've created, it has its own configuration file. We have to tell it if we want something other than the default, which is the root volume. Okay, so we've created a new volume, we've created a config file, and we've even created a snapshot for this new volume so that we can see what that looks like. So let's interact with it a little bit. As you can see, let's do a snapper -c data1 list. Okay, so we got our snapshots there. Now, where does that actually store? Where are we seeing these actual files? Well, when we were looking at the snapshots or the root volume, it was right off the root volume in a .snapshots folder. If we do an ls on the, let's do AL just to make it easier, and data1 on the data1 volume, sure enough, there is a .snapshots directory there. If we wanted to, we could interact with our snapshots by going into that folder. In this case, we're just going to delete our partition configuration for that particular snapshot. We can do it by just deleting the files, or there's a tool for it. It's under Snapper for data1, and delete config. Okay, and now if we do an up arrow and we list that, you'll notice the snapshots are gone from that directory. And if we wanted to, we could go in through the snapper tool and take a look at configurations as well. So there you have it, us working with snapshots, creating another directory, a new volume, creating a new config for it, writing our own snapshots, reading what snapshots are in that volume, and so forth under SUSE Linux Enterprise. Software libraries can be configured in SUSE Linux as well. In order to really work with libraries, though, we have to understand what a shared library is, the kind of differences between static and dynamic libraries, as well as how to configure those libraries to be in effect on a Linux box. So let's talk about shared libraries first. Libraries are an easy way or an easier way to allow written code to be reused, which results in smaller programs as that code doesn't always have to be included with them. It can come from a different source and exist on a machine and be used by multiple programs instead. Now, these pieces of code are in what are called shared libraries. Now, to use them, you link to them either in your code when you build them or when you run the program. So you can use both methods. Now, libraries are stored by default in the /lib directory or the /lib64 directory, depending on whether they are 32 or 64-bit binaries or libraries. Some examples. If we looked under the /lib directory, we can see that there is a library out there, an ELF file. It's 32-bit. It tells us information about it and the way that it was built and so forth. We can also see under the lib64 directory, there is a similar file, but it's built specifically for 64-bit, so we can see those differences between them. So what is the difference between a static and a dynamic library? Well, Linux systems have two different executable programs. We have statically linked and we have dynamically linked. Statically linked executables contain all of the functions that they need inside of their binary. They are complete programs and they don't go external in order to get any information or to borrow any code from anyone else. Now, the advantage of that is that the programs will likely work without the need of you installing any additional libraries or packages elsewhere. They're designed simply to be self-contained. Now, that can be attractive, but it's not always efficient. And dynamically linked executables result in smaller programs. They require the functions from external libraries to run, which is a dependency, but dynamic linking permits a package to specify which libraries are needed in order for that particular package or executable to run. And many programs can share a single copy of the library instead of loading the memory with a whole bunch of different copies of the exact same code. Obviously, better if we can reduce that. So, when working with dynamic dependencies or libraries, we have to use a tool called LDD. Now, this is a tool that allows you to see where various libraries are going to require other, or various executables will need various libraries and where they are. So if the primary doesn't use a library and you use the LDD command, it tells you something like in the bottom box there, not a dynamic executable. Now, the output of LDD can be explained. With just a little bit of work, you can see how these things work out. LDD space LN. What does that give you? That's the Linux version of here are the shared libraries that we're using. Now, if we go and look at one of those, that's the next box down, libc.so.6. What is that? Well, that's pointing somewhere else. That gives us information about something else. Okay. And where is that? Well, we track it down. We can see where all of these are going. We can see how they're related to each other and so forth. So LDD by itself, useful, especially when doing debugging and looking for information about why a particular program won't run or is having troubles running on an individual system. So how do we configure libraries? Libraries are generally affected, dynamic libraries are affected by two different configuration files. There's the in the etc directory an ld.so.conf and an etc ld.so.cache. If you go and take a look at that first file, you'll see something like, here's the location of the libraries, here's some information or some places that you should additionally scan, in this case, include file that we want to use as part of our configuration. Now, that .conf file tells us where those things are located, but there's also what's called the dynamic library cache. When we load a program, one of the things that developers and a lot of times consumers of a program are interested in is how fast does a program load. Now, there is a tool called the ldconfig command that processes the information in the ld.so.conf file, that configuration file we just looked at, and it creates the necessary links and pieces that are needed in the ld.so.cache file. This cache file makes it so that the load times can be faster because it is, as the word implies, cached and ready to be consumed. We can see what's inside the cache at any time with an ldconfig -p. And if you change anything inside of the ld.so.conf file, you need to run ldconfig again as root to make sure that the cache gets rebuilt as well. And this should be consistent logically if you think about it. So, what if we want to load a particular library? If we're going to run from let's say a different location than the standard one, you need to go and grab that. There are tools that can grab libraries from those locations. And you can do that by setting a path variable to specify a search path for executables. Specifically, ld_library_path is a colon separated list of directories that should be looked through when going for or looking to include shared libraries that may not be in the default path. General server health. In this section, we're just going to look at understanding the monitoring tools that are available when administering a SUSE Linux Enterprise server. So let's talk about the monitoring tools that are out there and what they're used for. One of the key components of monitoring a SUSE Linux box, or really administering one, is creating a baseline. Now, what is a baseline? A baseline is a definition of what normal looks like for a server. If you don't have a baseline for a server, how can you compare its behavior now to what it was when it was installed, let's say 6 months ago? So creating a baseline is very key to understanding the health of a server because each one will have its own profile. Now, what would we include in a baseline? Well, information about the boot, or what hardware is going to be included, or what hardware should be included. What utilities would we use? We might use various hardware scraping information to go and gather information about what hardware is there. We might also want to know things like what processes are running at any given time on a machine. What should be actually running on a particular machine? And of course, what is the impact of the load or the things that are running on a particular machine on that? And what does that mean as far as performance and those who are consuming services off that machine? So creating a baseline requires a lot more than just saying, okay, this is what top looked like, 15 minutes, every 15 minutes for the first 30 days that this ran. That might not be very helpful. So creating a baseline is a key task. It's widely overlooked, but very important in giving you this is what normal is supposed to look like. Now, what might we monitor going forward? We've got our baseline. Let's say we've created a baseline. This is what defines this server. Well, we're going to look at the boot process. If that's a thing that you do, and a lot of servers do get booted from time to time, even if we hope it's not as often as certain other operating systems. But we want it to be very obvious that the boot process is something to keep track of. What about the CPU? What is the CPU doing? Have you ever lost a CPU? Have you ever had one stop functioning on you? A core that misbehaves? These are all things that could happen. It also could not really be hardware related. It could be that someone has put too many processes and tied them to a certain core or a certain CPU. We might also want a profile on what's going on in RAM. Are we consuming our RAM all the time? Are we constantly heavily into swap? Do we need to add more RAM? Not that RAM fixes everything, but it does fix some things. What about storage? Are we filling up our root volume? Are we keeping track of how full we are? What about the network? How does that machine connect to the internet or connect to our network or connect to X other machine or whatever? So these are things that we have to keep track of as we interact with a SUSE Linux box and monitor its process. Now, during the boot process to start with, what would we do? We would press escape during the boot to see what information. By default, it pops up a pretty little graphic and it shows you that the machine is booting. But sometimes you want to see what's underneath. Hitting escape gives you that. We can also, after the machine is booted, log in and type dmessage as is listed here. We can view entries with the journal_ctl -b. And we can view the varlog boot.log file as well to see what's going on. These are all possible things that we can do to see what's going on with a boot process, and then, of course, compare it with a baseline. What about the CPU? Well, if we look at the proc CPU info file, it will give us information about it. What about the way that the host is configured? How is the kernel compiled? What information do we have about the kernel? Something like uname -a might be a starting point for figuring out when something doesn't match up or something is not performing right. This is just basic information, but these are things that you can monitor to compare to a baseline to give you information as to what's going on or what's different about a machine from, let's say, the other 3 machines that are running the exact same services and aren't having a problem, but this one is. And maybe it's the CPU. Maybe it's a different version. What about utilization of the CPU? You know, people laugh about the use of uptime. One of the greatest things that comes out of uptime, it's a very quick way for you to see the load averages. Remember that load averages are a way of describing how busy was the CPU and any given cores, how busy were they over a minute, a 5-minute period, or a 15-minute period. And keeping track of how busy it's been and looking at that can be quite useful. Now, there's also, of course, the go-to tool for monitoring on a SUSE Linux box, top. We can see processes, CPUs, memory profile, utilization. We can see how a particular process is actually functioning. We can sort by particular processes, users, and so forth. There's a great deal of information from top. Top is a great tool for monitoring what's going on with the CPU at any given time. It is also good at working with memory-specific items. So what do we need to watch? Well, the 2 primary things we look at on a Linux box, usually the amount of RAM that's being used, and of course the amount of RAM that a machine has, and its relationship to swap utilization. So moving stuff in and out of swap, if you do it too often, can be a real detriment to the performance on your machine. So what commands would we use? Well, the free command, which gives us a list of how much free memory do we actually have out there. And of course, top, as we described earlier, also gives you information about what is going on as a memory profile. So let's look at a couple of other tools that are particular to memory, and that one of them is VMstat. This is a tool that allows us to see since boot time as well as over a particularly defined interval of what has changed. The columns that we see specifically for swap, the SI and SO columns in the middle there, kind of describe what's going on. If you're not seeing a lot of SI and SO values, let's say 0, like is shown here, then how much swapping are you doing? In this case, none. But it's interesting that these numbers will change as you do something like compile code on top of a machine and give it something hard to do. Another interesting thing is that along this top row, all of those values are specific totals since boot. And you can see that information again. There is also the BI and BO values. These are blocks in and blocks out, read and write values per second. So BI is read, BO is written out. Additional items we monitor. The hard drive. Storage is always going to be one of those concerns. Now, if you want to monitor individual disks, you could use the smart CTL command. Or if you're working with a RAID, you might use MD-ADM, the multi-disk administrative tool, for looking at and working with those environments. And each of those are going to be used, again, in comparison with a baseline to help you to understand why is performance or how is performance different from when it was working correctly. But again, requires that baseline to have been made. Another tool that we use for storage performance is YaST, which shows us the writes per second, the reads per second, and a bunch of other information like how long does data stay in cache before it's written to disk. We can see some of that stuff, and when you get experience with it, it's interesting to be able to read the I/O profile of a particular set of disks or a disk device. Now, the last thing that we look at is the monitor of the network. There are multiple tools to do this, and we're not going to cover all of them, but there is the IP tool, which is great for seeing whether a link to the network is defined, an IP address is defined. We also have the ETH tool command for interacting and changing hardware-specific settings, duplexing, frame size, and other things can be worked with using ETH tool. You also have the iptraf command for seeing what's going on, and of course the SS, which is a replacement for netstat, but has a lot of the exact same features. In fact, a lot of the options are identical, but they produce usually a better organized and easier to read set with additional information about them. So we really like SS, and netstat has been deprecated. It's still there, might not be next time. Now, there's one more tool that we use when profiling a machine, and this is a tool that is used by our support department here at SUSE. It's called Support Config. And the purpose of Support Config is to make it so that instead of us having to get secondhand onesie, twosie pieces of files from people where they send us a portion of what is going on their system with a log file or a configuration file, you run the Support Config command and it will grab a lot of information and then zip it up, and then you can just send it to one of our techs, and our techs can open it up, and without touching your machine, they can usually diagnose what's going on. This is extremely useful. Also, because of the transparency of the tool tells you what command was executed, with what arguments, and then the output. So you can also use it as a learning tool when trying to figure out how to do troubleshooting. Now, it is a bash script. It's owned by the support utils package, and it gathers system information. You should be aware of what information it is using. You can go and read our documentation on it, exactly what's going to be pulled and under what circumstances. Sometimes that is sensitive. Now, the goal is to gather needed information and save it into a single directory. Now, the files will end with a .txt. It makes it so that editors will work on whatever platform you're on. And then it tars and bzips the file to compress them, making them quite small. They're mostly text. And we can actually, if we want, change the default naming convention, which is NTS, the host name, the date, and the time. But you can go in and change that using the -B if that's what you need. Now, they are organized. Each file is arranged by topic. It has a header. It has the command that was executed and the output. And then, of course, what do we actually put inside of these support config tarballs? Well, you've got RPM validation, you've got service status, we've got informational commands, we've got configuration files, we've got log files. It gathers as much information as possible so that we can troubleshoot that and work with it. This is transparent. You can take this information and it can become your tool as well. You can gather them up and then diagnose a machine without being remoted into that machine all the time. You can just pull it to your machine and open it up and take a look at it as needed. This is an example of support config being run. Just execute support config and it will go through and gather information and put it in that format as described. Monitoring, analysis, and tracing. In this topic, we're going to talk about the monitoring methods that we use to extract information on a machine. as well as the optimization tools and the processes we use to optimize a machine, and then to use some of these tools in effect to define and help us perform those tasks as an administrators. So first of all, what methodology might we use when doing monitoring? Well, there's kind of an overall idea of how to do system optimization, and they require that we have a good tool set, a list of things to do, including monitoring, analysis, and tuning of the system. And then we have to apply that not only to the system as a whole, which is all of the processes and applications running on it, but we also have to look at the way that the CPU is being interacted with, the memory, the storage, the network, and so forth. So there's a lot of components here, and it's interesting that we can use a kind of a methodology in order to extract this information. So first of all, what components would be monitoring? Well, we can break them down into different areas. It could be general system optimization. It could be CPU specific functions. It could be memory specifics. It could be I/O specifics. It could be network specifics. And then, of course, we always have to look at the way that applications are running on top of things as well, because, as you know, applications don't always behave exactly as we would prefer. So what are some optimization tools that we would use to work within this methodology or this set? Well, we would need tools that would gather information for us. We would also need something that would help us to digest the information. So tracing, analysis, using baselining tools, doing differentials on files, comparison, and the basic components that would go into that. Those are going to need tools to work. And then we have to have something that can implement the changes that we are recommending in order to resolve issues that may be on a machine. Now, there are two varieties of tools out there. There are those that are supplied by the system, and as a result of it being Linux, there are a lot of tools that can be used on the operating system to extract information like this. We can also create our own scripts or looking in the /proc or /sys directories in order to extract information about either the hardware or software or any application that is running on a machine. So what is the actual act of monitoring? Monitoring is gathering information. It could be hardware-specific information, and the reason for that is hopefully very obvious. We want to maximize the hardware itself. We want it to do its best. Now, there are going to be some realistic things here. Obviously, we don't want to spend hours and hours and hours to get a 0.01% increase in performance in most cases. That might be big in some specific areas, but in a lot of cases, that's not big enough to invest lots of time. So there needs to be some realistic ideas there too. Specifically, we might also use monitoring to look at performance, to find what is normal, which is what we defined as a baseline. And then after we put a heavy workload, some machines are very busy first thing Monday morning, say from 9 o'clock in the morning until say 11 o'clock in the morning. When people come in from their weekend, they start working, and this application that's served up by our SUSE Linux box has to be able to respond appropriately. And what is appropriate? You need to know what that is. So that performance baseline has to be done. And we need to know what it looks like when it's under load. And of course, we need to do that over a periodic set of time so that we know that over time it looks like this. And during certain stretches of really hard work, this is what it looks like. Again, part of monitoring a system is knowing what normal is. Now, what is analysis? Analysis consists of several things. It is a way of systematically approaching our environment. And usually this is the method that a lot of people will follow. So we follow a defined process. As an example, a machine is not connecting to the network appropriately. What's the first thing you check? Well, various people would say different things, but a lot of times the first thing that people will say is check the physical. Is the cable plugged in? How many times have you run into a machine that's not behaving properly and network cable simply wasn't plugged in? That's a problem, but that's part of a process that you've defined. Check that physical first. And a systematic approach allows you to make sure or to avoid some of the mistakes that might be made from a more haphazard investigation. And a lot of times we document these so that people won't have to go through the same pain we do when we first discover that something is a problem and we find a method for figuring that out. Now, obviously, there's a couple of things that we also need to do with analysis. We have to know the tools that are associated with analysis. If we do not, what happens is we don't actually allow ourselves to extract the right information. So being aware of the tools is also very important. We also need to understand the architecture and the subsystems that we're going to be affecting. We also need the effects of subsystem interactions and the potential impact on performance and or stability of a particular machine just by interacting with those subsystems. Sometimes you want to do a profile of the disk I/O, but you don't want to do that in the middle of the day when everyone else is using the system. You might wait until a more optimal time in order to do those kinds of things. So when we're doing analysis, we can use a systematic approach, but we need to know how to use the tools and what tools are available to us and exactly the impact of this analysis is going to have on a given machine. Now, sometimes the thing you don't want to hear is that you're going to have to do a little bit of extra work. And the reason I mention this is good analyzers take good notes, organize them, and they save everything. The reason for this is you don't have to reinvent the wheel or refigure out how to solve something every time. Sometimes you go months or even years without seeing the same problem twice. I don't know about you, but I don't remember everything. Writing things down and keeping them where I can go and refer to them helps. We can also automate performance tool and application tests so that we can reliably repeat them. So in other words, we never skip a step and get an artificial report on how performance is impacted by something. We also almost always want to use tools with the lowest impact or very low impact on a machine. We don't want to artificially increase the load on the machine if we don't have to. We also need to learn to trust the tools. After especially we have some experience with them, we can start extracting which tools produce the best results. We then use the knowledge base of other people's experiences. I've heard of this website. It's called Google. They have this great thing where people who have done things report what their experience was and other people come and learn from it. I know, excuse the sarcasm. It's a good thing when people share their knowledge of how something works or how to fix things. And same thing goes when troubleshooting a machine. Now, reference the internet. This is the last one. It's actually the same point. But I just want to point out that your local people asking your coworker why something doesn't work is okay, but sometimes you do need Papa Google to go and to help you figure out how to resolve an issue. Obviously, validate the source before you proceed because sometimes people give bad advice on the internet. May have heard of that. So we've talked about monitoring, we've talked about analysis, but we can kind of break it down a little bit deeper. There's also investigation process that has to go on. When we are trying to determine what's going on a machine and whether it is doing what we expect it to, we have to start with that baseline. In other words, we have to have previously collected information that is useful to us so that we can compare it to where we currently are so that we can diagnose the problem appropriately. Generally, we start with the largest circle and work our way in. What do I mean? We determine the general problem first, and then we research an ever-shrinking circle until we zero in on what the problem is, and then we resolve the issue. This requires some tuning, where we change the system configuration to affect performance in what we hope is a positive way. It does require us to continue to monitor and analyze the information of what's going on. As we tune something, we should know its impact. This is also what we call an iterative process. We make a change, we check to see its impact. We make another change or further that change and see its impact. That's how we tune for best performance. It requires that ongoing monitoring and analysis. So, what are some basics with tuning? System tuning is an art, and it requires attention to multiple areas, and the people with experience generally develop a sense of what it is supposed to be doing. This also goes the same for people who monitor servers. Generally, when people spend time watching a certain subset of machines, they generally have a basic understanding of what it's supposed to be doing and when it's misbehaving. When we are working in this parameter or paradigm of tuning that requires us to carefully monitor and analyze information, we make small changes and we look for problems in that process and we tune that machine as we go. Balance tuning is critical to optimum performance. Now, what is balance tuning? We tune things in most cases one thing at a time, but we'll make a change, we'll see its impact. And if there are multiple pieces that affect the thing that we're trying to tune, we'll make a change to, let's say, piece A, see its impact, and then make a change to piece B and see its impact with change A also being implemented. And then we balance that to see if we can get the best performance out of it. Now, it's going to be impossible in a lot of cases to tune for every workload on a single system. You can't tune I/O to be high performance and at the same time also make sure that all network traffic is 100% perfectly tuned as well. Well, you can, but there are going to be some limits on how you can get those two coordinated with each other. You might also have problems where you need high throughput, low latency, or high latency is okay, but even higher throughput on your storage environment. So we have to watch those things. So where do we focus our attention? We disable things that we don't need. If we don't need the GUI, make sure it's not running. Get rid of the extra stuff that's going on a machine and tune based on that and see how that affects your machine. Now, the kernel itself has its own tuning functions to work with. The Linux kernel allows a boot time and a live tuning of its parameters. At boot time, we add things usually to the Linux line in grub, and we set those values. But we can also go into the proc directory and make edits that will change that behavior. We can also insert modules, remove modules, and do other things that will change that. And there are some pre-tuned ideas for general server workloads under SUSE Linux. By default, it is tuned that way. We attempted to set a kind of balance thing, but that doesn't always work. Sometimes you need a very specific tuning, and you can do that with the various tools out there. In this section, we're going to look at the optimization process under SUSE Linux Enterprise. Optimization is usually performed by an iterative process. In other words, we go through the work of gathering information, then analyzing the various subsystems, and then tuning those subsystems based on what our goals are. And then we watch to make sure that those changes accomplish what it is that we want or are moving us in the direction we want. We then go through the process again iteratively, in order to further improve based on, again, our overall design goals. So over and over, we work through this process in order to improve the way that the system performs. So in order for this to work, though, we need to use specific tools in order to work with and push through these iterations as we improve the system. And one of the primary packages for doing that is the SysStat package. Now, this is an interesting package because it contains benchmarking and performance data capturing tools from everything from the hard drive to memory and throughput and all sorts of things. And so SysStat contains SAR, SADC, SA1, and SA2, which are very useful for tracking information, SADF for space. You've got your IOStat tools, MPStats, and ISAG. So SysStat brings with it a bunch of tools that will be of value when iterating through the optimization process. So what are those various tools that we mentioned? Well, SAR collects and saves information specific to the system. In other words, in order to track what is happening on a machine, something has to be recording it. SAR is designed specifically to capture that kind of information. There's also the System Activity Data Collector, the SADC. SA1 and SA2, although very similarly named, one of them collects information for you to track and to gather, And SA2 will write that information to a report. So one is for the collection and one is for the summarizing and export or dumping that information for consumption. SADF gives you information for database loading or graphing. You also have YaST, which is great for CPU statistics, I/O statistics based on devices, partitions, and then even network file systems can be tracked through that. You also have the mpstat command and the ISAG. mpstat reports individual or combined processor-related statistics. So how's the CPU actually functioning? And ISAG is an interactive grapher allowing you to create visualizations of how performance is being collected performance data is being collected by SAR. So there's also the sysctl command. Sysctl is useful because it gives you the ability to tune kernel parameters at runtime. And so you can use it in a dynamic method. And usually this is an exploratory type method where you want to see what the impact of a change is on a system, but you don't want it to be permanent. So you use it as a dynamic. So it looks at the changes and then you gather information and then analyze it to see if that's what you want. But then, of course, you can also use sysctl to set it as a static thing so that the next time that the system is restarted, that machine will inherit those changes that you've defined as well. Now, what other tools do you have out there? Well, we've looked at SAR and the tools there, but there's TOP as well, which we've kind of mentioned before, but TOP is very important because it is, for a lot of administrators, it is the first tool that will be cracked open when looking at what's going on with the system, for good reason. It kind of has a dashboard. It tells you what the CPU's been doing, the load values. You can see what memory's doing, how much swap is being consumed. And you can track individual applications to see what they're doing as well. So there's a lot of information that can be gathered here as well. Now, IOTOP is similar to TOP in what it's trying to accomplish, but zeroing in on input-output or disk I/O and reports information. There's an IFTOP, which is specific to network traffic, again, giving you information specific to network interfaces and something similar to the TOP interface. Not identical, but does give you some commonality. There's also other tools that you'll use when doing analysis, specifically strace. strace is great for seeing how an application is interacting with the system. strace allows you to basically profile an application. What is an application doing? How is it interacting with the system? And where can improvements be made? strace is used frequently by application developers when they're trying to track why an application is doing something. But of course, this also falls into an administrator's lap as well, so that they can say, which application, why is an application causing issues on my system? Where are the bottlenecks here? And so very useful for tracking information. You can use various settings, the -C option as an example to get the count time, the number of errors, the number of calls that are being executed. And you can use a verbose mode, and of course you can dump that to a file and track that information for later consumption as well. strace is typically used to determine if the blocking factor for a disk I/O is a particular application. And it's also, of course, can be used to track memory information, how much memory allocation is being done. In other words, you will see a lot of strace when we have, well, if you're tracking memory leaks, that could be a reason to have it, as well as many other things. But strace has a lot of functionality and a lot of use cases, especially when optimizing. You can start tracing after an application, so you don't have to start the application with strace. You just find the process ID of that application and then use the strace command with the -P and the process ID, and it will track that application in order to see what's going on. Obviously, since you're tracking an application and viewing how it's using and talking to not only memory but other system resources, you need to run it as root in order to be effective. All right, in this lab, we're going to add in some software development components and then put a load on a server and monitor it as it's under load. So give us some semblance of real world watching and monitoring of a SUSE Linux enterprise machine. To begin with, though, we need to add in a software repository to do this. And we're going to do this. We're just going to add this in, and we're going to click the add button, and we're going to do DVD, and it's on I think it's on SR1 that we want. It is. And then we're just going to grab the development tools module, and we're going to add the legacies module as well. We're just going to use a couple of different tools here, and we'll just go ahead and add that. We're just adding our repository in. All right, so we've got the new repositories there. And now we're going to add in the actual tools. We've got the modules added. So it's a software single. And we're going to go in and we're going to add base development under patterns, just our base development in order to get that running. Let's see, base development just right down here under development. We're just going to add that in, and we just click accept, and it will go ahead and add in the stuff we need and push that across for us. Okay, so we get this software added, and then we're going to install a couple of things. We're going to install kernel source. We're going to add a couple of other tools, and then we're going to have it start compiling a kernel. And while it's compiling the kernel, we'll take a look at the load numbers with top and kind of watch how that is affected. We'll talk about that impact, and it should give us a good idea of what this is supposed to look like. So we've got that installed. We're going to clear this, and let's just do a top. We're just going to leave this running. We'll just put this over in the corner like that. And then we're going to open a new window here. We'll just expand it out just a little bit. And we're going to install a couple of things. Let's do zipper non-interactive. And we're going to install BC and kernel source. So we're going to install two things. So it's going to go ahead and get that. And there we go. Okay, so those are installed. That's going to take just a minute. And then we're going to change into the user source Linux directory, and we're going to take a peek at what's in there. So with being in that directory, we're going to create an old config. Basically, it's just going to say grab the current configuration, and we're going to use that from the running kernel. And then we're going to start a make job on creating a kernel, and then come back to the top and look at what is there. So if we do a user source Linux and we do a make old config. All right, so it's looked at the existing running kernel. It's created a config file for us to work. And then we're going to do a make -J3 BZ image, just to put a load on the server. Okay, so this is going to make it do some stuff. Now we're watching over here on the right side. I want you to pay attention to this load value, this first one up here where my cursor is. I'm going to highlight it so you can see it. We're going to watch those numbers right there, and they're changing. They're going up. Now, if you remember, load is how much work is being done over an average of time. One being for a particular number of cores. So each core represents one. So right now it's saying that, hey, we're working those cores pretty hard, and you can see those numbers are consistently going up, and that will continue to do that. Now we're going to wait so that the first value here gets over the value of 1, which we've already got. So we're good. We can go ahead and kill this process. We just wanted to force the system to go up like that to make it work. And then, of course, we're going to clean up after ourselves. So make clean. We'll go ahead and remove all that stuff that we compiled but aren't using. And notice again, come back over here to top and notice that this load value is going down. Okay, and again, that's over the last minute, the average load on the CPUs over the last minute. All right, so top is the go-to tool for most administrators when working with a system and wanting to monitor what's going on. Why? Well, you can see CPU, you can see memory, you can see I/O, you can see swap, you can see all sorts of other things across your system from one tool. And you can get it to update according to your needs. It's very configurable and very easy to read after you get a little bit of experience with it. So top, very good at doing what you needed to do. All right, so that's the first step. Top is one tool for monitoring. Let's look at a couple of other tools that might be of use. If we were to install, let's do a zipper SE for SysStat and see if it's installed. So it is not. So we're going to do a zipper in SysStat, and it's going to go ahead and install that for us. And we're gonna change some parameters on the server itself. We're gonna reboot this machine, this virtual machine, and we're gonna add a restriction on the amount of memory that it uses. It has, I believe, 2 or 4 gigs of RAM assigned to it. We're gonna cut it down to like 768 and see what that effect is on that machine. All right, so here's what we're gonna do. Let's clear this up. We're going to just reboot this machine and wait for it to come back up, and we're going to break in and assign 768 megs of RAMs here. So we highlight the one we want to edit, we press E, and we scroll down to the Linux line, and we give it a value of mem equal 768M. All right, we've got that added. Then we can do a Control X, which will save it and boot with that value. And we're just going to wait for the machine to come back up. It's going to take just a moment while we do that. Okay, so the machine is back up. We need to see what values it came up with. Make sure that that 768 memory value that we gave it was effective, that I didn't typo or cause a problem there. So we could do, there's a couple of uses or ways to do that. We could do something like a CAD on proc command line, and it tells us, oh, yep, sure, there's the value that we had in there. So that's what the Linux value was when the parameters assigned when the kernel was loaded. We could also do a CAD of proc meminfo and look at the memory values, and we can see, if we scroll up here, you can see that the mem total, free values, etc. across there, and that lines up with about what we expected. Okay, so we've got our memory available. So let's work with a couple of tools to just kind of see what's going on here. Let's do a vmstat1 and just see the values that are scrolling by. And now this is going to change. We're going to specifically watch these swap in and swap out values, because we're going to be playing with some memory intensive things, and we're going to see these values climb. So we were looking at load value previously, but now we've restricted memory, and we're going to see what memory does. So when we get in here, we're going to change to that user source Linux directory and do a make -J10 BZ image, and we're going to watch those SI and SO values climb. If you can see, they're already jumping. You can see them just climbing up really fast. And again, we kind of expected that. We limited the amount of memory, and then we said, hey, do something intensive, and so that's what it's doing. So we see that it's going, and we just wanted to demonstrate that you can see what the impact on a machine is, heavy load can be. So we're going to go ahead and kill these things. We're going to kill both of them. All right. So they're not actually doing anything that's important, but with the vmstat tool, we can see how memory is being impacted by a heavy load as well. So let's make clean on this just to clean up our mess. So we've looked at the load on the CPU. We've looked at the load on the memory. Let's take a look at hard drive info and see what we can get there. So let's go and do a zipper in info on a tool called Bonnie. Now, Bonnie is a tool that gives you benchmarks specifically with the file system. And since a hard drive is usually sitting underneath there, this is a good tool for working with that. So let's go ahead and install Bonnie. Zipper in Bonnie. And we'll just get this added in. And then we're going to use tools like LSBlock and YaST and then Bonnie itself to take a peek at what's going on. So if let's clear this up and open this up just a little bit more. Give ourselves a little more play area. Let's do an LSBlock. And this lists the various block devices that are on this machine. We have 3 what looks like CD-ROM or DVD-ROMs. And then we have some other block devices, hard drives of various types that are in here as well. Now, let's go ahead and over here on one of these, we're going to start an YaST command to monitor the input-output to these block devices. And we're going to tell it which device we want it to play with. Let's do VDA2 in this case. VDA2 was our root device, if I remember right. If you look over here, you can see that. It is a root device. And if we do a Bonnie-S 1024, this will start generating some stuff to the hard drive. And we can see the impact as these values start to go up. Specifically, we're looking at these await commands. You can see what's going on here as these will change. Let me expand this even more just to give us a full pull across there. Let me do it again. And just watch. You can see these values climb. Await's going up. You see that? And this service TM is going up as well. And you can see those being impacted by what Bonnie is doing as it's testing I/O. Okay, so we've got another tool, YaST, that we can use to see what's going on with the hard drive. Now, Bonnie is useful just for simulating traffic on your drive, and that's why we installed it. The other item that we haven't looked at is the network. So we've looked at CPU, we've looked at memory, we've looked at hard drive. Let's take a look at network functions and just to take a look at what we can do there for tracking it. Now, all of these things would require a lot more effort, a lot more time in order to become an expert at working with them. This is just the groundwork for knowing that these tools are out there and knowing how the impact on your machines and your environment. You're going to have to spend time looking at them in order to really see what is normal and what is not normal under your circumstances and the loads in your environment. Okay, so let's look at networks now. Let me just go ahead and clear this YaST. So we're going to install a couple of tools. We're going to do a zipper in of net tools deprecated, just to get the tools that we want here. Because netstat is technically deprecated, but the reason we're installing it is so that you can see that the new tool that is replacing it is called SS, and it gives you a lot of the same functions, even with the same options, but gives you more information actually, and so it's why it's been deprecated, is SS really is moving forward in what it's capable of. So let's start with just a simple comparison. If we do a netstat, and type enter, it spits out a bunch of information. It shows all of your connections, where they're being touched and so forth, what files and so forth. Now, SS, on the other hand, does a similar thing. It just gives a little bit different format for it. So the point here is that SS gives you the same information. It just uses a different format. And in a lot of cases, it gives you more information. Now, if we do a netstat-patn, it gives you the listening services that are going on there. Let's go and do the SS with the PATN, and notice that we get the same thing pretty much. It's just got a little bit different format for displaying what's going on there. All right, and that was for TCP. Let's look at sockets with additional information. So what we were doing before, but we're just going to put an E on the end. It just gives us a little bit more information on it. And we can do the same thing. You'll notice pretty much the same type of information again being spit out, just with a different format. Let's take a look at UDP. So we do netstat dash PAUN for UDP and SSPAUN. Okay, and again, we can see those differences. And if we wanted additional information, again, you can put the E on there and to see that. Okay, so the point is netstat is deprecated. Some people have complained, well, netstat is a core utility. It's a core function that's been used for many years. Why are you getting rid of it? Well, it's deprecated. It's not completely gone. And secondly, the SS tool actually gives you more information. It's fairly obvious SS has a reason to be used, and we should probably be looking at that going forward. So there you are, working with and monitoring a SUSE Linux box in our environment. Let's talk about control groups. In this topic, we're going to look at what is a control group, just defining it, but we're also going to look at kind of the model and what it's sculpted to look like. We're going to talk about the rules that go into working with C groups, and then, of course, how do you actually administer a C group? So first of all, let's understand C groups. C groups are kernel control groups. They're a kernel feature that is designed to allow you to aggregate or partition tasks or processes together and affect those aggregations and partitions as a whole by executing a single command against those control groups. Now, tasks are by default organized into hierarchical groups, and that doesn't change within a C group. C groups can be configured to show the specialized behavior of what's going on or implement a specialized behavior as well. They can also be used to help in tuning the system to make best use of the available hardware and network resources based on the load and the work profile of that particular application or machine. So some terminology that we need to define. First of all, a C group is the creation of an association or a virtual grouping of tasks with parameters for one or more subsystems. Those subsystems can be things like memory or disk or CPU. And we can set up a hierarchy where one C group is arranged as a subordinate to another one. And each process that is running is generally referred to when working with control groups as a task. So what is the C group model? When looking at the C group model, you have to understand what a process model looks like. Now, a process on a Linux system using systemd is going to be a child process of a common parent. So in this case, systemd is the common parent or the highest level process. Everything else is a subordinate or a child process of some nature below that. The Linux process model is a hierarchy and a single hierarchy where all processes descend from that single parent. And the Linux processes inherit the environment and other attributes from its parent process. So that's a Linux process. The C group model takes and allows us further division of that Linux process model into a C group model, where C groups are similar to processes in that they are hierarchical, and child C groups inherit the attributes from a parent C group. There is a fundamental difference between them, though, in that many hierarchies of C groups can exist simultaneously on a system, and when you interact with one of them, you don't necessarily interact with all of them. So multiple separate hierarchies are defined because we want to allow them the ability to interact with subsystems in a different way. Now, a subsystem represents a single resource. So when we talk about a subsystem in a C group model and modifying the way that a group of applications in a C group interact with a subsystem, we're saying something like the CPU is a subsystem, and this C group, let's call it C group A, interacts with the CPU, but only interacts with the cores 1 and 3. It doesn't interact with cores 2 and 4. And we can put the same kind of restrictions based on the type of subsystem we're working with, like memory. So when we're talking about C group design, the design allows for a simple C group usage. In other words, by default, it's simplistic. If you want to, you can make it very, very highly customized and make it work the way that you want it to work based on the needs of the applications and on that particular machine that you're configuring. So there are two types of subsystems when we're working with C group subsystems. We have the isolation and special controls, like allowing us to say CPUs 1 and 3 are being used, but CPUs 2 and 4 are not being used by a particular thing. We can work with network namespaces in such a way. We can do things like freezing and unfreezing various processes. And then we also have resource control, like how much CPU time is allowed within a C group. So we can say this group of applications is higher priority, therefore they're going to get more CPU time than other applications, and so on. So C groups give us control at a level both for isolation, but also for throughput and access to those application components. Here's a simple designation or graphic of what it looks like from a hierarchical standpoint when working with C groups. Now notice that this is all underneath the sysfs C group directory. We see underneath that a designation for C group, then the group itself, and any parameters and subgroups that might be affected by it. Here's another way of looking at it. If we look at the proc mounts file, cat proc mounts, and we grep for C group, it will show you the different C group items that are currently listed and available. So let's talk about those subsystems a little bit. What subsystems are there? There's the block I/O, which allows us to set limits on input-output access to and from block devices. We have the CPU subsystem, which is specific to the scheduler for providing task access to the CPU. The CPU accounting, which allows us to give us reports on CPU availability, and CPU set, where we're assigning individual CPUs and memory nodes to tasks in a C group. We also have devices, which allows device hardware specific access to devices by tasks, and then the freezer, which allows us to suspend and resume tasks inside of a C group. We also have memory as a C group. How much information do we get, or how much memory do we get access to within a C group? And then we have network specific subsystems as well. So let's talk about the C group rules that might be used within the Linux C group environment. There are relationships between subsystems, kind of hierarchies of control groups and tasks. So we need to remember that system processes are called tasks in C group terminology, even though tasks may be, in most cases, relegated to items that are happening within a shell in a user world. So don't forget, system processes are still called tasks inside of a C group world. And there are 4 rules governing the relationships between the subsystems, the hierarchy of C groups, and the tasks themselves. Rule number 1, a single hierarchy can have one or more subsystems attached to it. This should be relatively obvious. If you're creating C groups, you are going to be putting them into a segregated environment where you allow applications within that to either have or restrict access to various items, such as memory, CPU, and so forth, those other subsystems we defined. Rule number 2, any single subsystem cannot be attached to more than one hierarchy if those hierarchies have different subsystems attached to it already. In other words, you can't do 2 at the same time. I think the graphic is fairly obvious here. Rule number 3, a task cannot be a member of 2 C groups in the same hierarchy. That doesn't mean they can't be in 2 different C groups of a separate hierarchy. And a single task can obviously bridge that. It just makes it so that tasks don't get confused and there's clear, obvious rules as to what access they have. Rule number 4 is that child tasks automatically inherit C group membership of its parent. It's then independent and can be moved to different C groups as required. So there are your 4 rules. C group functionality, however, you need to wrap your minds around the idea that a task can only belong to a single C group under a hierarchy. But once you move outside of that hierarchy, it can exist elsewhere. And several subsystems can be grouped together so that they affect all tasks in a single hierarchy. It is also possible to refactor a hierarchy. In other words, move tasks around and even move relationships between hierarchies in order to adjust the functionality within those C groups down below. So how do we administer C groups? We've defined our terms, we've set some rules now. What can we do and how do we do it? Well, C groups are administered by either creating subdirectories in the subsystem directories we defined under SysFS, or changing files in those subdirectories after we've created them. Now, systemd places each service into its own C group by default, and it's under a default hierarchy underneath systemd. The primary tools for administering C groups in SLE 15 are the mount and systemctl commands. However, there are other tools available. To view processes that belong to a service, the command is systemd-cgls, so list control groups. The mount command can be used to administer C groups using mount-t, talk to the C group, the group name, and then the location. The subsystems can be called individually with the mount command. None in this example is the C group name. The systemctl, which is a tool specific to interacting with systemd, can be used to set limitations on C groups, as systemd has inherited many tools inside of its environment for working with C groups, since it defines C groups for each of the tasks that are launched. Here are some examples, working with slices and services and defining our limitations based on the C groups that are inside of systemd. In this lab, we're going to work with C groups and the various tools that can manipulate and change settings for individual C groups. We're going to start by installing some utilities that will be used in our lab. So as root, we're going to run a zipper non-interactive in of the CPU set utilities. This will include the cset tool, which we'll be using extensively in this particular lab. So if we do, now that we've got that installed, a cset shield to give us an idea if any shielding is on. As you can see, there isn't any going on, so we're good. We're ready to move forward. So let's start by setting up a new C group. So cset set-c, we're saying use processors 1 through 3, and we're going to put it in a C group called CPU set 1. Okay, so we've created that, and we can do, to see what available C groups are out there, we can do a set list, and this will tell us we have our root one, and then of course a CPU set 1, which we just created. Notice that it also lists the CPUs that are being used. We can see that here under the CPU column. The root one is using all 4 of our processors on this virtual machine, and the CPU set, since we defined it as 1 through 3, well, those are the CPUs that are being used for it. Now, we're going to check, because of the NUMA architecture out there, you need to know whether NUMA is engaged while you're working with C groups. So if we do a NUMA CTL hardware, this will tell us whether it's out there and functioning. Only node 0 is available, so this means that we don't have NUMA on this particular environment, in this environment, so we don't have to worry about NUMA specific functions. So let's come back and take a look. In the SysFS C group CPU set, we can see CPU set 1 is listed there as a directory, and as a result of that, if we look at the contents of one of the files down below, we can see the assigned CPUs for that. Although we could also see it with that CPU set list command just a different way of doing it. So if we do a cat of the sys fs c group CPU set 1 and CPU set.cpus like this, it tells us 1 through 3. Okay, so when we're working with scripting and stuff, there are tools that can go and grab this content out of these files and we can work with that. Now, what if we want to change some values for CPU set 1? So we want to change the C group. Now, all we're doing right now, we haven't put any processes into our CPU set 1. We've only defined the parameters that are going to define that C group. So we'll look at that stuff later. But for now, let's just look within this. If we do a C set -s CPU set 1, we're going to create a new one. Oh, whoops. Before we do that, let's actually just change it. So set-c 1 and 3, right? So we're going to change the CPU numbers from 1, 2, and 3 to just 1 and 3. That are being used by the CPU set, and then we have to tell it which CPU set. Okay, so now if we do a C set -L, that would be the same as --list that we did previously. But if we do -L, you'll see that 1 and 3 are now being used instead of 1 through 3. Okay, so that gives us some idea of how to interact with it. Now, of course, we could go back and take a look at this CPU set.cpus, and we see 1 and 3. So let's rename our subsystem, CPU set subsystem, and make some changes, and then we're going to interact with the processes there. So if we use a C set-s CPU set 1, and we give it a name of new CPU set, then it goes ahead and it performs the rename for us. Okay, and now if we do a C set-L for list, you can see that that CPU subsystem has been renamed to new CPU set. And if we take and combine applications inside of this and use this as part of our C group, we then have access to the limitations and the capabilities that are defined here. So that's renaming it. Let's just go ahead and delete it. Let's say we don't need it anymore. It would be a C set-D on new CPU set. Whoops. I'm sorry about that. It's CPU set like that. Okay. And it goes ahead and removes that item out of the system. That's gone. So if we do a C set list there, we can see that we only have the root one. Okay. And that's what we want. We're going to create a new CPU set. We're going to call it top set. So C set-c 1 through 3 if we wanted to. And then we're going to give it a new name. We're going to call that name top set. Okay? So we created a new set called top set with CPUs 1 through 3. Very similar to what we were looking at before. Now, we can also create what are called a subset, or something below the top set, inheriting the capabilities and functions of the previous or the hierarchical set. So if we say we're going to create a C set-c3, which CPU? Only CPU 3, and we're going to call it top set subset 1. Okay? So we've created a new CPU set down below, and we can do something like C set-L-S because we're looking underneath the top set, and we can see the top set and the CPU set are a subset 1. Okay. All right. So we can see that. We can see the results of it. You can also use another command instead of specifying that you want to see what's inside the top set. If there are any subsets defined, you can use a recursive list. So C set-L-R, and as you can see, it tells you the path and it includes everything. Okay, so at the top we have the root CPU set, and then down below that we have additional items as well to work with. So notice, and this is interesting, if we do a C set-D for delete and we say top set, it says, hey, I can't do that unless you either delete the ones that are underneath or you use the recurse item when you're doing the deletion. So let's use the recurse option in order to get that. So C set-recurse -D on top set. And now it says, oh, wait, are you sure? In other words, you have to use recurse and you have to use the force. It's just to keep you from accidentally deleting them without meaning to. Okay, so we've got several pieces already built there. Let's take a look now at a couple other threads and processes that we can work with the cset proc subcommand as well. So we're going to create two new top-level CPU sets. We're going to call them test 2 and test 3. And we're going to give them processors 1 and 2 for test 2 and processors 2 and 3 for test 3. So they're going to share one CPU. So how would we do that? Well, if we do a cset set -c of 1 and 2, and we use that for test 2, so we've got 1 created. So cset set -c 2 and 3 for test 3. Okay, there we go. Now if we do a cset set -l-r, we will see all of those available to us. Okay, we got 2 and 3 in there. All right, so let's take a look at the processes in the root set. So we can use the cset proc command and -l-s and root, and what it shows us is all of the CPU. Let's expand this out so we can see it a little bit better. But what we're seeing is, let me redo that just to give us a little better perspective. So these are all of the processes that are running in the root set. Now, if we do a cset proc -l-s on test 2, what are we going to see? Nothing, because we haven't put any processes into that CPU set as yet. We can check the same thing for 3. So let's clear this and let's do a cset proc. Instead of -l, we're going to do s in test 2, and we're going to put inside of it a bash shell. Okay, so if you look at the return, it tells us we have put a process with process ID 445 inside of the CPU set defined as test 2. Okay, so now if we do a cset proc list of -s of test 2, what do we see? Oh, we see exactly what we just described. We've got bash running in there as well. And you can actually see that the command we just executed against test 2 as well. So we see those show up, and now we can see that we have added one in there. Let's do another one. So let's do a bash. Let's do a cset proc -l-s test 2, and there we go. We actually see an additional one. Now, why did that happen? Well, when we executed this bash command up at the top here, this one up at the top, it opened a new shell. And then when we executed this, we actually saw the bash command, and we see this. But we're inside of that bash command. So then when we execute bash, there's a nested bash session. So when we list it again, sure enough, we can see the additional bash in there as well. Okay, so that's executing commands inside of a CPU set, so we can assign which ones they're associated with. Now, we can go beyond that though. Instead of executing or starting a command inside of a CPU set, what if you want to move a command into a different CPU set? Well, we can do that too. So if we do a cset proc -l-s again, whoops, I forgot test 2. Okay, we're just going to grab one of these. Let's take the child process ID. So that's this one, the 464, and let's move that into test 3 CPU set. So cset proc -m-p 464-t test 3. Okay, and now if we do a cset proc -l test 3, look at that. We have successfully moved that process underneath the other CPU set. All right, so if you remember, we're just using different CPUs. That's how we've assigned this out. All right, since it was moved, it keeps the same process ID as well. Now let's move the other bash process to the root CPU set. So instead of over to a sibling, let's move it to the other CPU set, the root one. So if you do a cset proc -m-p of 445 and -t because we're moving it to root like this. There it is, and if we were to go look, we could probably find it. But probably another way to do this is, instead of doing test 3, if we just look at test 2, you'll notice that there aren't any tasks actually running inside of it. Okay, so we've successfully moved some things around. We've created them inside of there. Let's move an unbound kernel process from the root CPU set to the test 3 CPU set. So cset, let me clear this so it's just a little more obvious. Cset proc-l root. Oh, let's actually pipe that through head and just take a look at the ones at the top there. You'll notice that right at the top, it has the list of the number of tasks running. As you can see, that's 464 tasks. Okay, we can see that value. So if we do a cset proc-k-f root to test 3. Okay, so what did it do? What we said was, take all of the tasks that are can possibly be moved. Actually, we just said move all of them. Move all of them to test 3. And so it did that, but it complained because some of them, in this case 53, were impossible to move. And so we couldn't do that. So we can now move them back, and we probably should do that. If we do a cset proc mk force of test 3 to root, we move them all back. We push them all back into their environment. And if we wanted to, we could go in, and there's a file in the etc directory. Let's just show you what that looks like. Oops. Big.conf. Oh, sorry. You have to add that. If you go in, you can add into a file. It's the cgconfig.conf file. You can put in how you want things arranged. Now, if you need more information on that, there's a man page for the cgconfig.conf file, and you can go in and look at that and look online. There's lots of information on it. But there you have it, working with control groups in a basic format, at least giving you an idea of how you can assign which processors to work with and how to move a process between those CPU sets so that they're grouped according to parameters that you define on SUSE Linux Enterprise.